So this is our fourth lesson on acids and bases. What we've talked about so far is what your quiz encompasses, and at the end I'll make sure you're very clear on what your quiz assesses, and your quiz is next week. So we've talked about definitions for acids and bases. We've talked about properties of acids and bases. We also learned how to calculate pH, pOH, proton, hydroxide ion concentration, and also concentrations of strong acids and strong bases, as well as masses when provided with volume. So hopefully you feel very comfortable with those sections so far. What we're going to talk about today is how to name acids, both binary and ternary. We're going to review how to name bases. You already know how to name bases and write chemical formulas. You just may not have realized that they were bases at the time. So sometimes when you teach chemical formula writing and naming, like we learned at the very beginning of the second 9 weeks, you also learn how to name acids and bases. I find that to be a little bit too much for the kids, so I like to just do a separate little lesson on the naming of acids and bases. So first we're going to talk about binary acids. And what does the prefix bi mean? Two. So these acids have two different elements in them, an H and a nonmetal. When you name these, the prefix for a binary acid is always hydro. So anytime that you have an acid that starts with hydro, it's binary. It's going to be H followed by a nonmetal, and you may have a subscript after the H. I'll show you how that's determined. The suffix for a binary acid is always ic. So it's going to be hydro something ic acid. The element that's paired with the hydrogen is what's used as the stem. And the stem is the same as what you learned when you learned how to name ionic compounds, and also, for the most part, covalent compounds. So chlorine has a stem of chlor, fluorine, watch the spelling, fluor, iodine, iode, bromine, brome. So in those cases for group 17, you're just taking off the INE to get the stem. Then it gets a little trickier. Sulfur, the stem is the same as the name of the element. Tellurium, the stem is tellur. Phosphorus just becomes phosphor, so you're going to take away the us. And nitrogen, you're going to lop off the OGEN. So those are the stems that we're going to be working with. Those you need to know. You'll have to memorize them. When you name the binary acids, again, it's, I think I left this in by mistake. Oopsie. Now they're gone. That's what you have in your notes, right? Okay. So when you name the binary acids, it's hydro, stem, ic acid. So hydrochloric acid, hydrofluoric acid. So any binary acid, an H followed by a nonmetal, is hydrostemic acid. So for the next one, you see H2TE. And that 2 came from the charge on a telluride ion. And what do all binary acids start with? Hydro. You take the stem, and then ic acid.
That's it?
That's it. So what would this last one be? Hydro, iodic acid. And you very often work with hydrochloric acid in the laboratory. You've seen that chemical formula before. You've seen the name of this acid. So if you always use that as your basis, I think you'll be very successful with this type of naming and writing chemical formulas. And if you don't have a periodic table out, you'll want to take one out. If you want to grab one of mine, that's fine. That will help you tremendously today with the naming and the writing of the chemical formulas. The other thing you're seeing with the acids is you're seeing AQ for aqueous. When you've got these acids, they're aqueous, that is dissolved in water. Because, for example, if you had gas here instead, then you wouldn't name it as an acid. You'd name it the way you learned previously, hydrogen iodide gas. So a little bit different there. So when you change it to aqueous, that's when you've got your acid. And be very careful here. When you name these off, for example, gas or a liquid, you go back to your ionic naming, even though these are covalent compounds. When you've got H there, it's a little bit tricky. If you want to write the chemical formula for the binary acids listed below, this is very straightforward based on what you learned previously with formula writing. Again, if you see hydro, you know it's binary. So hydrochloric acid, this one's already done for you. You're going to have proton, chloride ion from group 1, swap, drop, reduce, and eliminate, hydrochloric acid, aqueous. Same thing with hydrobromic acid from group 17.
Are they always going to be aqueuses?
For the acids, yeah. Hydroiodic acid. And one point I definitely want to drive home, although this class seems to have a pretty good grip on this concept, we mentioned that there are 8 strong acids. A strong acid ionizes completely. Of the 8 strong acids, 3 of them are binary. And these are the 3 binary acids that are strong acids. So that's a point I wanted to make. Hydrofluoric acid, also binary from group 17, is not a strong acid. It's actually a weak acid. The next one says hydrosulfuric acid. The fact that it says hydro tells you you've got proton and sulfur is in group 16. So what would its charge be if it formed an anion? 2 minus. So the 1 goes there, the 2 goes there, hydrosulfuric acid. So if it says hydro, it is binary. Hydrophosphoric acid then, again, you've got this. Phosphorus in group 15 would have what charge if it formed an ion? 3 minus. And your chemical formula for the acid would be what? H3P.
Do we have to write aqueous or not?
I'm just signifying you have an acid as opposed to hydrogen phosphide.
That would be triprotic acid.
That is a triprotic, but it's kind of a funky one. And we'll get into that too. Monoprotic, 1 ionizable proton. Polyprotic, more than 1. This would be diprotic because you have 2, triprotic because you have 3, and we'll hit that in a few minutes. Hydrofluoric acid then would simply be HF. And even though that's from group 17, it happens to be a weak acid. So these are 3 of the 8 strong acids. So the binary acid's pretty straightforward. So if I said to you hydroiodic acid, you'd write HI. Another grouping of acids are referred to as the ternary acids. And when you learn about 3, very often you think of the prefix tri, like a tripod, a tricycle, trifocal. But another prefix for 3 is ter. And you may or may not have learned about
Tertiary consumers.
Okay, tertiary consumers. I was thinking tertiary structure for proteins, but if you did tertiary consumers, that's perfect. Also 3. Did you learn about primary, secondary, tertiary, quaternary structure with proteins? Primary structure, just the amino acid. Secondary structure, the way it folds, like alpha helix, beta pleated sheets. No? Okay, so that may be an AP Bio. Sometimes I'm not clear on what you do at what point. And in biology, we used to do it, but it's, the bio curriculum has certainly changed since I taught it. But a tertiary structure actually helps explain, like if you have curlicue hair like mine, the disulfide bonds that hold the curls in place. All right. In any event, ter means 3. So with the ternary acids, they contain 3 elements. You're going to have H. This subscript of A is dictated by the charge from the polyatomic anion. X, this can typically be a nonmetal, but it also can be a metal. Definitely oxygen, and N is the number of oxygens you have. The prefix and suffix that you use here depends on how many oxygens you have. Oxygen will also always be the last element in the series of 3. This is, at first glance, going to be a little tricky. I'm going to show you a trick that will make it less tricky so that you understand the ternary acids. Bear with me for a couple of minutes. The most common form of the acid has the suffix "ic", and there's no prefix, so you can't confuse it with the hydrochloric acid where you have binary. So the most common form is "ic", sulfuric acid, carbonic acid, phosphoric acid. No prefix. What's tricky here is the number of O's is not consistent for "ic". It's either 3 or 4. The easier way to do it, because of that lack of inconsistency, is to understand what always generates "ic". And that's what I'm going to walk through here with you. I'm going to write these out and work through this so you can see the linkage. I'm just going to indicate to the left of the chemical formula, I'm going to indicate the polyatomic anion. Then we have the chemical formula. And the name of the acid. So I'll say acid name. So the first one I gave you is H2SO4, again aqueous to indicate the acid. I'm going to focus on the polyatomic anion. SO4 2- is a sulfate ion. The prefix 8 in the polyatomic anion always becomes "ic" in the acid. No prefix. We've got S for sulfur, and this is going to be sulfuric acid. Let's do a few of these. The next one is HClO3. My anion is ClO3 1-, which is a chlorate ion. And this is chloric acid. So how do we approach this one?
I know freeze and nitrate. So it's nitrate, right?
That's correct. Good job. So 8 always becomes ick. And then the last one indicated is H3PO4. So I go after the polyatomic anion. What anion is that?
Phosphate.
Phosphate ion. And this is, be careful because this is, the stem is phosphor, so this is phosphoric acid.
What if you had, like a perchlorate?
We're going to get there. But if you have perchlorate ion, it becomes perchloric acid. So 8 always becomes ick. So if 8 is ick, then ite actually becomes OUS, and that's where we're going. And since you started to get there, I'll put the rest of this trick up. We say in chemistry there's a disease called adic itis. So 8 becomes ick, and ite becomes OUS. And the ite form has one less O than its 8 form. And that's what you're going to see here. It says if a second acid is formed containing the same 3 elements but having one less O, the acid is given the suffix OUS, and again, no prefix. So this is sulfuric acid, one less O is sulfurous acid. This is chloric acid, one less O is chlorous acid. Now, if you don't know the common form, it's a little tricky, and as I said, with the common form, you either have 3 or 4 O's. Sulfur and phosphorus are the ones that primarily have 4 O's, but there are some other ones too, like chromate, so it does get a little bit tricky. So in this next section, if we take the same approach where we have the polyatomic anion, and we have the chemical formula, and then we have the acid name, in the first one we have H2SO3, and SO3 2 minus is a sulfite ion. And that's something I do want to make clear. Yeah, I did write ion there. Never mind. Okay, we're good. We're good. We're good. So ite becomes OUS. So this is sulfurous acid. In the next one, we've got HClO2, and again, these are aqueous ClO2, 1 minus, is what ion? Chloride ion. And so this is chlorous acid. Ite becomes OUS. So in the next one we have HNO2. NO2, 1 minus is what ion? Nitrite ion. Oopsie. I think I saved it. And the name of this acid is nitrous acid. And H3PO3. PO3, 3 minus is phosphite ion. And you have these on the back of your periodic table. Some of you probably know a lot of them. That's something you really want to get down cold over the summer if you're going to AP. Ite becomes, so we have phosphorus acid.
Just phosphorus acid.
Phosphorus acid, yeah. All right.
How come like when people say like arsenic, they don't say arsenic acid?
So you're talking like arsenic poisoning?
Well, like, because wouldn't an arsenate, wouldn't A become ick? Wouldn't it be arsenic?
But not
acid?
all acids exist. So just because you have a polyatomic ion doesn't mean a polyatomic anion doesn't mean that there is an acid that encompasses that, or that there's not to say that a proton or more than one proton has to bond with that polyatomic to generate the acid.
Or like what about when people say arsenic?
Like arsenic poisoning. It doesn't necessarily mean it's the acid. It could be a salt with the arsenate ion. So the question becomes, what is arsenic poisoning? And it's actually, I'm pretty sure it's the salt. Let's look that up during the break. It's an excellent question. Let's look it up during the break and see exactly what that is. Some of it may not,
So not everything that ends in 8 that's a polyatomic ion can form an acid.
not necessarily. Yeah, let's look this up during the break and get a better grip on it and see if it's actually a salt or more like acid poisoning. I mean, you actually treat it with an acid to try and alleviate some of the symptoms, so that leads me to believe it's not, because you wouldn't treat an acid with an acid. But let's see exactly what that is, and we'll look that up during the break. I was flipping a few things. I'm not sure what the district's going to let me check, because, you know, sometimes they block stuff when you deal with poisoning or even DNA or anything like that. So, but we'll take a look. That's a great question. All right, So 8 becomes ick and ite becomes OUS. And you started to ask a question previously in regard to per. These are not as common, but they do exist. If a third acid is formed where you have the same 3 elements, but one less O than the OUS form from the ite form, then in addition to the OUS ending, you're also going to use the prefix hypo. Hypo means less than. Somebody who's hypoglycemic has low blood sugar. A hypotonic solution has less solute than what surrounds it. What other words have you learned with hypo? Hypothermia. So when the body is too cold, below typical body temperature of 98.6 Fahrenheit. So hypo means less than. So one less O than the ITE form. Generally speaking, with the hypos, there are only 2 I can think of. You're just going to have one O anyway. If you look at the back of your periodic table, ClO1 minus is hypochlorite ion. So then if you link it with the proton, you get hypochlorous acid. Again, ite becomes OUS, one less than the OUS form, hypo. What's not on the back of your periodic table is IO minus, which is a hypoiodite ion, but you still could infer the name of the acid pretty easily because it has one less O than the iodite form, so this is hypoiodous acid. And then on the flip side, if you have one more O than the common form that we did at the beginning, common forms end in what suffix? 8 becomes ick. So if you have one more O than the common form, you're going to use the prefix per, which is short for hyper. Hyper means more than. Somebody who's hyperglycemic has high blood sugar, diabetes. A hyperactive child doesn't sit still, like what I have in some of my classes. So hyperthermia, that's when your fever is just too high. You have a fever because your temperature's too high. So per, more than. And this is the most common example. HClO4, a strong acid, perchloric acid. The other one that's also a strong acid would be this. And what would be the name of this one? Per-iodic acid. So those are really the only 2 I can think of. The other ones don't form, but that's also in the name game. And what I tried to do here was make you a very small table where I had the element or the family, the number of oxygen atoms in the common acid form, again, is typically 3, but phosphorus and sulfur is 4. And I gave you the chemical formula and the names of those common acids. But if you remember that 8 becomes ick and ite becomes OUS, you'll be very successful naming and writing chemical formulas. So let's look here. Again, BO3, 3 minus is borate ion, boric acid. NO2, 1 minus is nitrite ion, ite becomes OUS, is nitrous acid. Focus here on the PO4, 3 minus, which is phosphate. So what's the name of this acid? How about this one? Focus on the polyatomic anion. IO3, 1 minus is iodate. So the name of the acid is iodic acid. This is also a strong acid and ionizes completely. This is the only strong diprotic acid. Focus on SO4, 2 minus, which is sulfate. Raise your hand and tell me the name of this acid. Go ahead, Alexa. You got it. Good job. Sulfuric acid. This one's a little unusual as well. CrO4 2- is the chromate ion. And HClO2, ClO2 1- is chlorite ion. So this is chlorous acid. So ite becomes OUS.
Can you have dichromic acid?
Yes. H2Cr2O7, and that one's really weird because you got 7 O's. All right, so the naming, pretty straightforward. The writing of the chemical formula, I think, will be pretty straightforward as well. I'll write these on paper so you can see the derivation. Carbonic acid, it's given to you, but I'll go over it. Ic comes from H. So a carbonate ion, I'm going to pair it with proton and carbonic acid. I've got nitric acid. It came from 8. Nitrate. Pair it with the proton. Nitric acid, also a strong acid. The next one is hypoiodous acid. Now this one, I don't give you a hypoiodite ion on the back, but you know how to do this because if you have hypo, how many O's do you have? 1. And the only ones that form the hypo are going to be from group 17, so you'll have 1H. Sulfurous acid. OUS comes from ite or ate? Ite. So you'd have a sulfite ion, proton, and here's sulfurous acid. Now perchloric, again, per is pretty straightforward because you will have 4 O's, but there's a perchlorate ion listed, and you've got perchloric acid. The naming and the formula writing of the acids, I think, is pretty easy once you practice, and I've got an additional classwork for you to provide you with more practice. There's online practice as well.
Why would for the hypoiodous acid, why would there not be a -1 superscript?
If you were putting it together, you'd have that, but the 1+ and the 1- compounds are neutral. Does that answer your question? Okay, good. All right, so the name of acids pretty straightforward. Takes a little practice. I do like to do it separate from naming that we did back at the beginning of the second 9 weeks. Some people do it all together, but I think it gets to be a little tricky. The naming of bases, you already know how to do. You just didn't realize they were Arrhenius bases when you learned how to do this. So bases that are Arrhenius are made up of a positive metallic ion and a negative hydroxide ion. You name them by the name of the element followed by hydroxide. And I guess this should say Arrhenius, because other bases are not named in this fashion, and I typed poorly. Oh, well then I'm glad you didn't see my bad typing. Ta-da! So for example, sodium hydroxide, potassium hydroxide. The only thing that could get tricky here is if you have a transition element that requires a Roman numeral because it can form more than one cation, or if you have tin or lead that also require a Roman numeral because they can be 2 plus or 4 plus. Otherwise, pretty straightforward. What would the name of this base be? Calcium hydroxide. And what about the next one?
Aluminum. Would it be tetroxide or hydroxide?
Hydroxide,
Okay, sorry.
because
I
it's
saw the first
ionic.
I just saw the 3, so I thought maybe it would.
Right, no, don't do that. The 3 came from the charge on the aluminum ion. This is the one that's a little bit tricky because this is cobalt, and you don't have to capitalize these. I see I didn't, and some of you will be upset, so I'll fix it. This one requires a Roman numeral because it's a transition element that can form more than one cation.
So it's cobalt 1 hydroxide.
It is cobalt 1, because hydroxide is 1 minus, so cobalt here has to be 1 plus. Electroneutrality. Alrighty? Pretty straightforward. And you already knew how to name bases, you just didn't know they were bases. The only other thing I want to mention is, again, you have a metallic cation here. If you have, kids often get confused on this, let me clarify it. If you have something like this, CH3 is not a metallic cation. This is actually methanol, which is an alcohol. Or you can say methyl alcohol. So this is not a base. Be careful there. All right, so let's take a look at writing the chemical formula. And again, this you know how to do as well. You just didn't realize they were bases. When you want to write the chemical formula, I'm going to do this on paper here. You've got lithium hydroxide, lithium group 1, hydroxide put in parentheses, 1 minus, lithium hydroxide. The next one is barium hydroxide, and the only thing I want to remind you of is if the number after the parentheses is not 1, you must keep those parentheses. That's the most common mistake that kids make. Sodium hydroxide, very straightforward. How would we write copper 2 hydroxide? What would be the chemical formula for that one?
Cu parentheses OH2.
You got it. And don't forget those parentheses. Good. And strontium hydroxide, a strong group 2 base, would be
SR parentheses OH2.
You got it. So you already know how to name and write chemical formulas for bases. There's nothing new there. Now you know they're bases. All right, the last thing we want to do in this section is also a review concept, but we're just going to link it to acids and bases. And that's one nice thing with finishing up with acids and bases is we do review a lot of concepts that we learned previously, and that's good as the semester exam looms closer and closer. What we're going to look at here is what happens when we react an Arrhenius acid, one that generates proton ions, or proton ion, and an Arrhenius base, one that generates hydroxide ion. When you react an Arrhenius acid with an Arrhenius base, you have a double replacement reaction in which you put the insides together and the outsides together. And you learned about this at the very beginning of the third 9 weeks, and that's where your semester exam begins in terms of content. What you always get when you react Arrhenius acids with Arrhenius bases is salt and water. The salt has different properties than the acid or base. What do you know about the pH of an acid? It will be less than 7. pH of a base will be greater than 7. If you react a strong acid with a strong base, which we're doing here, the salt will be neutral. Now, not all salts are neutral. For example, baking soda, which is sodium bicarbonate or sodium hydrogen carbonate, is slightly basic. That's why you neutralize acid spills with it.
Is that just a double replacement?
It absolutely is just a double replacement. So like I said, you already know how to do it. The only new piece is recognizing that you always get salt and water from an Arrhenius acid and Arrhenius base combining. So the salt has different properties than the reactants. This is usually pretty neutral, although it can be slightly acidic or slightly basic. That gets complicated. We're not going to go there. You wouldn't taste something you made in the lab, but if you did, it would have a salty taste where these wouldn't. And the salt doesn't react with metals. So again, if you have an Arrhenius acid with an Arrhenius base, you're going to put the insides together. You've generated this salt here. The outsides together, you've generated water. You're going to generate potassium chloride. Don't forget to formula write your products. HOH is water. You're always generating a salt and water. So let's go through these. I'll rewrite them here so you've got it. You want to predict the products of the following and then balance them. So the first one is done for you. Again, magnesium sulfate. Make sure you put the cation first, and water, and balance it. Let's look at the next one. You also want to be comfortable naming these now. You have sulfurous acid reacting with sodium hydroxide. The insides together, sodium sulfite and water. We've got phosphorus acid and potassium hydroxide making potassium phosphite and water. And I was a little too quick here because I didn't balance. Bad girl. So we've got to balance those. We've got 2 sodium, 2 sodium, 2 H's, and 2 more is 4. So you need that coefficient for the water. We've got 3 potassium. So what goes in front of the potassium hydroxide? 3. We've got 3 and 3 more is 6 H's, and we're balanced. Alright, next one up is hydroiodic acid and calcium hydroxide. Take a minute to predict that one. Well, actually, you walk me through one, and then we'll see if you can do it. All right, volunteer for this hydroiodic acid. Oh, you always volunteer. You better explain it as you go. Go ahead. Pause.
Can you tell me how you got the 2 in front of the H2O?
Here,
Yeah.
I've got 2
Oh,
H's
she had to balance it. Sorry. Never mind.
and 2 more. You good?
No.
That makes 4 H's. So I needed 2. 2 times 2 is 4. This,
And you put the 2 in front of the NA to balance it.
yes.
Right?
Here, you'll help me with this one. Ready? Oh, yes. Insides together, correctly formula written is?
I. Okay, CAI.
No, no, no.
What?
Calcium's in group 2.
No, it's.
Yes, it is.
Oh, LOL. Sorry, 2. This moment.
And what's your other product always?
H2O.
You got it. Now, we've got 2 I's here. So what am I going to put in front of the acid?
2.
Good. Now count the H's. I've got 2 and 2 more is 4. What goes in front of the water? You got it. See? All right, so tell me how to do this one. Go ahead, Ethan.
Okay. I did SRBR2
Perfect.
and then plus 4 H2O.
Hang on. Let's balance slowly. We've got 2 BRs here.
Which would mean 2H.
All right, now here we've got 2 H's and 2 more is 4. So what times 2 makes 4?
Just a 2.
So this should be a
2.
2. Very good. So just slow and steady and you'll be good. The next 2 problems require that you can write chemical formulas for acids and bases. So it says hydrochloric acid reacts with barium hydroxide. Raise your hand and give me the chemical formula for hydrochloric acid. Go ahead, Chase.
HCl.
That is correct. Good. Barium hydroxide, Andrew.
BA parentheses OH2.
Perfect. Now, products, Allison. Perfect. And the other product is always, you got it. Perfect. Don't be confused. Remember, HOH is water. So 2, 2, 2. And you'll get some more practice with this as well. And you'll have to be able to write these equations to be successful in the titration piece. All right, finishing up this lesson then. Something we've mentioned a couple times already is sometimes acids can donate more than 1 proton. They'll still do it 1 proton at a time, but if they have more than 1 proton to donate, we refer to them as polyprotic. So for example, polyprotic acids have more than 1 ionizable proton. For example, carbonic acid is a diprotic acid. It has 2 ionizable protons, as is sulfuric acid, chromic acid, and there are many other examples. Another type of polyprotic acid is a triprotic acid. For example, phosphoric acid or phosphorus acid. And if you look at these acids, for example, carbonic acid, this is actually a reversible reaction. It'll donate 1 proton at a time, and then its conjugate base can act as an acid, and that's why it's diprotic. It has more than 1 ionizable proton. But this is beyond the scope of the course. I know some of the other classes are doing KAs and KBs. I really think that's challenging for the honors kids. I think there's so much you can do with acids and bases. That I think is a little bit of overkill. If you're interested in KA and KB, I'll gladly show you how to do it. All I want you to recognize is that polyprotic acids have more than 1 ionizable proton as opposed to a monoprotic acid which has 1 ionizable proton. So you know how to name acids, you know how to name bases, you know how to react them together to get a salt and water. The naming of salts you already know how to do. We learned how to name salts. This goes over the acid and the ion, what they have in common. I already did that with you. You know how to name salts. These are far more complicated than anything you will ever see, so I'm not concerned there. You already know how to name all of these salts. For example, sodium sulfite, potassium phosphite. What's the name of this salt? Calcium iodide, strontium bromide, barium chloride. So you already know how to name salts. So for today, hopefully in this first lesson, you're comfortable naming acids, and you can name acids that are either binary or ternary. You know how to name bases. You also know that an Arrhenius acid plus an Arrhenius base. The Arrhenius concept is important because if you have Bronsted-Lowry, you're making conjugates, as we've talked about previously. So the Arrhenius acid and base, when reacted together, make a salt and water. And those are your goals for today. This reaction of an Arrhenius acid with an Arrhenius base makes salt and water. This is a neutralization reaction because you generate a substance that's typically neutral. And we will work on this concept more when we talk about titration in our next lesson. In regard to your classwork, so you know exactly what you're responsible for now, you already have classwork 4-4, and you already should have completed 1 through 10. Some of you also did 11 through what? 21. So some of you already did through 21. You now can do through 28. So 22 through 28. I'm going to give you a second classwork on naming. You want to be able to do the front page only. In regard to your quiz, which for you guys is not until next week, for your quiz, that goes through proton hydroxide ion determination. I drew that line in your notes, so you should be comfortable with how far to go. In regard to the classwork, you want to be able to do 1 through 19. But a word of warning, if you only prepare for your quiz for Wednesday, you're going to have an awful lot to do to get a high comfort level with what came after the quiz. So I would prepare for the quiz as if it were this week to make sure over the weekend you're mastering the remaining concepts. Be very careful there. That's the danger in postponing a quiz. Okay? Questions on anything we talked about when anything is?